Hello, everybody. My name is Narissa Suboy. I'm presenting a paper for my cloud computing class on Dynamo, Amazon's highly available key value store, a paper released by Amazon in 2007. It has many authors who are still, some of which are still at Amazon today and very high up, like Peter Volschel and Werner Vogels, who are top officers there today. Dynamo is a distributed key value store solution that Amazon developed for internal use only. And at the time this was published, it was still internal use only. So we're going to talk about why Dynamo came to be and what the need was for this solution. First, we'll start with some history. In 2006, Amazon launched Amazon Web Services, which had its first service, which was Simple Queue Service. In 2007, it shared that it had come up with Dynamo and that it was using it internally at the ACM Symposium on Operating System Principles. In 2012, they released DynamoDB, another like a built-up service of Dynamo in 2012, and then in present, they released a reflection and a look ahead of the service. This presentation is about the 2007 paper. So why Dynamo? Well, the paper tells us that at the time, client requests were sent through what they called a service-oriented architecture. Today, Amazon will say it's a microservice architecture, but back then they called it a SOA. And the paper says they had hundreds of services, and each request from a client was routed through multiple services and called other data stores and whatnot. And Amazon also prided itself in having very stringent service level agreements. And so you wouldn't want to have increased latency at any database call. And it would basically propagate all the way back up, and it'd be harder to meet their own performance requirements. This is something that one of the teammates on the paper described happening when they were calling a relational database. For example, if a simple SLA, a guaranteed customer 99% of the time gets a response within 300 milliseconds of peak client load for 500 requests per second, that means that every service it propagated through needed to be fast enough or faster so that the total time to complete the request met this requirement. This was very difficult when you had to call a relational database, and the authors in the 2022 blog shared that they were experiencing huge scaling errors as well when they were calling their SQL data stores, because there would be transaction locking and all the kind of issues that ACID principles will give you when you are overwhelming the database. So it just wasn't going to work. So they realized that not all workloads need to have the SQL level complexity and transactional guarantees, and they really wanted to lay off on the C, consistency, and ACID. So they identified the top operational requirements that they wanted to focus on so they could meet their SLAs, and they were reliability and scalability. They chose reliability as the number one because outages cost the company money and it eroded customers' trust in the service they were offering. And since they were a new service, building trust was extremely important. Then scalability, they were planning on continuous growth, so they needed services to be built so that they could just grow all the time. So what they realized was application state management was the foundation to both of these requirements. The application state management is keeping track of how a service's state is managed, and in a way that you don't have to go to a SQL database to find out what a service's current state is, what keys they have, what data they have in it. They wanted it to be faster. That's where Dynamo came from. So to meet these requirements, they developed the Dynamo distributed key value store. And it was a zero hop distributed hash table. So in distributed systems, we learned about finger tables and chord and all the multiple hops and things. This was a zero hop so that it was fast, and it had each instance or each network of Dynamo nodes had a single tenant, and they were managed by individual teams at the time. They called this a state manager. Some of the features, which in the paper are called design considerations, but now they're features, they really focused on having an always writable data store. That means even if there's failure somewhere in the line, the customer should always be able to add an item to their cart, or a change on a client side feature should always be written to Dynamo, regardless of who has the latest version or whatnot. And they did this with letting either the application, like the service, decide how to resolve the conflicts, with which we'll talk about later, um, or just have a policy that Dynamo keeps and says, okay, this was the last write, so this is the one that we keep. The other ones were incremental stability, so back to continuous growth. You should be able to add another host to your Dynamo network at any time without impacting the system. And every node had to have the same capabilities as its peers. So there wasn't a special node that only did one thing, like a master node or a daemon or anything like that. Everybody was the same. And heterogeneity, work distribution had to be proportional for all the servers that it was running on. And this was so that you could upgrade a node and it wouldn't affect the whole network of nodes. So the meat of the paper is talking about what structured the architecture, and it was really structured by problems, typical um, scaling problems, really, and consistency problems that they solved with fundamental distributed systems techniques. So I'm just going to overview them right here really quick before we go deeper. For partitioning, um, the technique was consistent hashing, which we did learn about in class, but with a little twist. And the advantage is incremental scalability. They achieved high availability for writes using vector clocks with reconciliation during reads, which is also something you learned in distributed systems. And it had the advantage that versioning was decoupled from how much you need to update. It handled temporary failures using a sloppy quorum and hinted handoff, and it recovered from permanent failures using Merkle trees to check timestamps pretty quickly without having to download a full objective history. And it used membership, and it solved the membership and failure detection problem by using the gossip-based protocol, where every node had a list of the nodes in its network, and they just compared every second and kept updating to keep everything fresh. It's just an overview. So for partitioning, Dynamo incrementally scales as nodes are added by partitioning data across a set of storage hosts, which are other Dynamo nodes. It uses a variant of consistent hashing to support this feature where instead of like a finger table, a node is mapped to multiple points in the ring of hashes. So when a new node is added, it's assigned multiple positions in a ring, and they call this virtualizing a node. So like you were responsible for a lot of different random areas for replicating, copying, partitioning. Um, and this improved availability of data when nodes are removed. And they were planning on like nodes being removed randomly or all at once, or they're just planning for a really worst case scenario in this design. And the number of virtual nodes a single storage node is responsible is automatically restricted by the capacity of a Dynamo node so that nobody was allowed to be overloaded. And then replication was obtained by those virtual nodes, so everybody had multiple areas they're responsible for on the ring, and while they were doing the partitioning, they were also copying the data at each of their hash locations that they were keeping track of. And this is just I'm just highlighting the importance from the last screenshot. data versioning is pretty interesting. So like they use Merkle trees to try to detect entropy or changes in the data. And with the Merkle tree, you can multiply two hashes together and they should come out to be the same. And that's how you know it's the same version. And like a big thing where earlier I said they kind of relaxed the idea of consistency. It's not guaranteed, it's eventual consistency. So it means eventually, using Merkle trees, they'll resolve who is which version and which version is the current version. This makes sure that things aren't locked up. And then the vector clocks keep track of what caused the different version of the same object, kind of like timestamps. And for very complicated conflicts, they left it up to the application or service to deal with those for mostly. And another thing is like your application who wants to write to their Dynamo network, they have to know which version they want to deal with. It's not up to Dynamo unless you give them a default policy. So there's a lot of customizing available for the services themselves. And get input is the most interesting one for me. So basically, they vary the reliability and the availability and scalability by letting you choose how big you want your quorum to be, or how many other nodes need to respond to you to confirm a put or write. So R is the minimum number of nodes that must participate in the read. W is the minimum number of nodes that must participate in the write. And as long as R plus W is greater than N, where N is the total number of nodes, healthy nodes, you can do your operation. So this is good. And when I say healthy, I mean if some of these are down, the whole thing just updates, but you can still do if your R and your W are set correctly, you can still do your writes even if some are down. And that's what they say, kind of like lazy quorum or sloppy quorum or whatnot. So here's an example of what I was saying. If you get 4 responses back, at least W minus 1 nodes responded, your put is successful. So it's a lot more flexible. Handling failures. So they handle temporary failures by the sloppy quorum that I just talked about, and also by replicating data across multiple data centers, which now we talk about like availability zones and things like that. But back then in the paper, that's how they put it. And handle permanent failures, they use the Merkle trees to find inconsistencies, to go back in time and reset data. And the Merkle trees, you don't have to download the full like tree and read through it from top to bottom. So it was faster. You didn't have to transfer more data every time you were trying to recover something. And then how do you know like where you belong if you're a node? They had an explicit method. So you had to literally log on in the client, a CLI, and directly shush into a node and propagate a membership change. And this was basically to provide an extra guarantee that nodes weren't like just willy-nilly getting added to a network. And then I already talked about how they gossip so that they know who's in the network. So the use cases at Amazon in the late 2000s, business logic specific. So how do you reconcile if there's a network issue and the cart had 0, now it has 1, which one is current? And then the timestamp based reconciliation, settle which was the last version of data, and then high performance read engine. So some people just use this to store data they're calling all the time just as a reference, and they weren't really taking advantage of the write, but it was just super fast just as a read only. So wrapping up, Dynamo lets you tune your number of nodes, read nodes, and write nodes to customize performance, availability, and durability for your application. And it met at the time Amazon's desired level of reliability and scalability, and it became the starting point for DynamoDB. And there are some slides at the end about what DynamoDB has become today, as well as additional slides on system requirements and more other things that the paper included that you can read. And thank you very much for your time.